This video is for page 5 and 6 of the conceptual questions for Unit 3. So number 17 asks us to, out of these 5 forces, which one or which combination is going to give us something that is in equilibrium, and if they're equilibrium, that means that the net forces are going to be equal to 0. So if we added B and D together, right, you add vectors head to tail, so you would take B, you would add D to it, and the resultant is from the beginning to the end, which essentially gives you 0. So that is adding B and D. If you add B and C, right, you would add B, and then you would add C, right? We've got B and C, and then if we add E to it, it would come back down, and it looks to me like it would end right where it started, and so those would add up to 0 also. For number 18, right, it says the free body diagrams show a force or forces acting on an object. Draw and label one or more forces that will cause the object to again be in equilibrium. So if there's weight down, then we need a normal force or a tension force or some force up that's equal and opposite to that, so that the net force in the y direction would be 0. And same thing with over here at B. If we have a force, if we have a force in the x direction, this pushing force, we need something in the opposite direction so that those add up to 0 also. So I said it was friction. Who knows what it is, but it needs to be to the left and in equal length to the force push. On number 19, if we have these 3 forces, right, adding them head to tail, we would get the force over, the normal force up, and then we would get the weight down, essentially giving us a net force that's down and to the left, so my force went up and to the right to cancel it out. I guess another way you could look at it is if you just looked at the forces in the y direction, right, if you have this and this, you would need to add in that much force in the y direction, and in the x direction, if you have this force, then you would have to add in a force here. So essentially we would be combining those green forces, right, the up and the over, and so the force that's needed to again get an equilibrium would be this force to cancel out the others. So same thing in B, right? If we have this kind of looks like it's on an incline, so if we have the weight down and the normal force up, we know that in a situation like this, right, that the weight y would cancel the normal force, and then you would have the weight x pulling down the slope, so we need some sort of force up the slope to cancel that force down the slope of weight x, cancel that out. Moving on to number 20. Elevator travels upward at a constant speed. Well, this is the key word. If it's a constant speed, that means all the forces are equal to 0. So is the tension greater than, less than, or equal to the weight? It has to be equal to the weight, right, because they need to add up to 0. So as far as explaining it, right, the tension is equal to the weight of the elevator because according to Newton's first law of motion, so this is your justification, an object in motion will remain in motion at a constant speed if the net force is 0, right? So I've justified why I know that it's equal. In part B, if it's traveling downward and slowing down, that means because it's going down, right, that means it has a negative velocity, and it's slowing down, which means it has to have a positive acceleration, which means I know that there has to be a positive net force, so therefore the tension has to be greater than the weight because I need a net force that's up. Right, so the tension must be greater than the weight because according to Newton's second law, so this is me justifying my answer, right, I'm giving proof, a net force will cause an object to accelerate in the direction of the net force, and I guess I could have expanded a little further and said this object is accelerating up, so the tension must be greater than the weight. Looking at 21, right, we have the figures show free body diagrams for an object of mass m. Write the x and y components of Newton's second law. Write your equations. Sorry, it's like 10 o'clock. Write your equations in terms of the magnitudes of forces F1 and F2 and any angles defined in the diagram. So, you know, if you're looking at it in the x direction, right, if you're thinking this MAX, you're basically saying the net force in the x direction, right, is going to cause your mass to accelerate in the x direction. And the net force in the y direction will cause your mass to accelerate in the y direction. So looking at our 21, right, the only thing in the x direction is F3, so that's the net force. In the y direction, you have F1 and F2. I've made F2 negative because it's acting down, right? It's acting in the opposite direction of F1. So looking at our second example, right, where I'm including these angles, if this F1 is here, we know that this would be F1x, right, and this would be F1y. Well, it says that we need to put it in terms of the angle. So we know that, let's say in the x direction, right, we know that the sum of forces in the x direction is going to be F1x plus F3x, and essentially we would say that the F1x is negative because it's to the left, right, and F3x is positive. Well, we can't say F1x and F3x. We have to put it in terms of F1 and F3 and leave those angles in there. Well, if this is our angle, because it's adjacent to F1x, we know that the cosine of theta 1 would be the adjacent side, F1x, over the hypotenuse of F1, giving us that F1 cosine theta 1 equals F1x. Right, so now instead of me putting in F1x, I put in F1 cosine theta 1, right? And I make it negative because it's to the left. So you're going to do the same thing with F3. Because the exponent component is adjacent to theta 3, it's going to be cosine. In the y direction, right, if cosine gives us the x component, then sine is going to give us the y component. Right, so we know that F1y here, right, is pulling up, so it's positive. F3y would be this component. Right, it's pulling up, so it's positive, and F2 is pulling straight down, so it's negative. Hope that helps you out on those 2 pages.